I've started recording. Thank you everyone for coming to this afternoon session, the third session of the series of lectures. We are officially, I guess, hump day. I think Jan wanted to make an announcement about some of the things we can do in building up this community. So Jan, can I give it over to you?
Yes, most definitely. I think one good thing to do. So to everyone, first of all, thank you for the birthday wishes. I really appreciate that. And we've said
Sorry,
before,
I just want to jump in there. It is Jan's birthday today. I forgot to mention that. Happy birthday, Jan.
Thank you very, very much. As I said before, I've never had so many birthday wishes scroll down and at one time. So thank you very much. If it's someone else's birthday, happy birthday to you too. It's the best day to have your birthday, 28th July. I think it's the best day of the year. But I'm biased. What shall I say? So let's start sharing the screen.
In the meantime, can I talk about the LinkedIn and
yes,
Twitter?
Let's do that.
So it'll be great if all the participants here who have LinkedIn accounts and Twitter account create your own YouTube video on what you've learned in data science, and then link us to that. We'd love to hear about what you've done and what you've learned so far. My Twitter handle is @KanshUK, so KANSHUK. What about yours, Jan?
Okay, so I'm hoping my screen is being shared. So I'm going to put out there for everyone, create your own YouTube channel and put some lectures or talk about your work and tell us about it, and we can link on it and grow your channel. Number 2 is, yes, you've heard Kanshu's Twitter handle there, and LinkedIn is the other one. So let's do, did you give your LinkedIn?
My LinkedIn
is quite easy.
Search for Kanshukan Rajaratnam.
Yeah, and I mean, that's the same for all of us. So, I mean, anyone who sends me, and I've had quite a few, and I'm glad to be connecting with all of you, but certainly get your LinkedIn profile up because that helps a lot. And let's grow this community on LinkedIn. And then, of course, the best and the easiest to get news about data science and all the tools, the open tools that we use, just follow all these big accounts. But so for Twitter, follow me as well, and I'll follow you back. And for me, that's just there we go, Doc Jean K, DOCJUANK.
Can you also give them mine?
That at the top. Let's do for Kanshu. Yours was Kanshu?
Kanshu K.
There we go.
LinkedIn, you can just search for my name. I'm the only Kanshu Rajaratnam in the world, so it should be easy. There's another birthday that I want to mention. Maybe I should mention it tomorrow. The birthday is only tomorrow. The school turns 2 years old tomorrow.
Hey.
So what? A bit younger than you, Jan.
just beaten by a few years. I'm not far away.
Yeah.
Excellent.
With that, I'm going to put myself on silent or on mute. Please do create a YouTube video or a YouTube channel and upload what you've learned and what you think about data science. Spread the word about data science. Also, do it on LinkedIn and Twitter and tag us as well. Thank you. Over to you, Jan.
Thank you. Yeah, let's grow this community. And there's one good way to learn data science, of course, is just get the experience and start a small little project and do it. And the other way is to try and explain it to someone else. That's when you know that you really understand something. It's when you can explain it clearly to someone else. So let's start with the exciting stuff. These first 2 days, of course, we had this introduction to Python, which brought us onto this level of being consciously incompetent. We know that it exists now. And we looked at just trying to understand the story that the data is trying to tell us. And if you have some of your own data, I hope you've tried it on your own data and started to see some patterns and interesting things pop up by just doing summary statistics and visualizing your data. And that's all fair and well, but now we get to something much more interesting. And what we're trying to understand is the meaning in our results. So we can do all sorts of calculations on our data, but we have to attach some meaning to those results. What does it mean? And perhaps even or equally or perhaps slightly more important than that is the uncertainty in our data. How uncertain are we in those results? And coming from a scientific point of view, of course, we deal in those kinds of things as scientists. We don't deal in the absolutes of other kinds of systems We want to see the data, we want to see the analysis, and we want to know how unsure we are on that data, and certainly that comes tomorrow. So for today, it's really understanding through the process of resampling. We use that term, I think, just before 2 o'clock, but this idea of resampling, how can we use just the data points that we have in our project to try and understand how likely it was, or how probable it was, would be a better term, of finding the results that we do. And a specific part of data science, of course, is inferential statistics, where we have this idea of a sample taken from a population, getting some results and inferring our results back to the population. And in many fields, that's exactly how it works, whether you're engineering and there's some apparatus and it needs to be calibrated and it needs to be tested every now and again. So you take some samples from it, and those samples better be within a certain range. Otherwise, that whole machine needs recalibration. We might take some projects at random from a production line and test them to see how long they work, and we'll get some results from that sample, and we infer those results onto all the product that comes off that production line. So whether it almost doesn't matter what field is, all of these things that we do in data science pertain and is important to us. But what we clearly want to remember is it is hardly ever do we deal with the whole population. A factory won't stop and take for one whole year, take all its production and send it for testing instead of selling that product. Or take some apparatus that's used in some laboratory offline for a year and just use it for testing. We take samples, and we want to understand the results that we get from those samples and how they pertain to the larger population, whether that's a machine, whether that's a bunch of organisms in a lab, or some chemical, or human beings, or it doesn't matter what it is. We take a sample and we need to understand how that fits into the bigger picture. So we'll say a little bit about randomness and sampling here, and sampling distributions and distributions as a whole. Now, at the end of the exercise number 9, stay tuned for that. Right at the end, I'm going to just delve a little deeper than the course really delves into distributions and statistical tests and the assumptions for various statistical tests. This is not a course on statistics per se, but many times we are going to analyze our tests with some well-known common statistical tests, and we need to know where they fit in as well. So that's going to be the bonus section at the end of exercise set number 9. So today, of course, we only have the 2, 7, and 9. And I'm just going to say something about the notebook in 8, but I really urge you to read the notes or play with the notebook or watch the lectures. So I can see, of course, because we've uploaded all these lectures, how many people actually watch the lectures. So I do urge you to view the lectures, but of course, if it's better for you to read the PDF, please read that. And more importantly than anything else, play with the notebooks. That's most important. So I'll say something about hypothesis testing, and then we'll go to 9, and there'll be this bonus section at the end of 9. I hope, I don't know if we discussed it before 2 o'clock or so. Let me just mention just again. So all these extra exercises and these notebooks that we do live here, I'll compile all of them and we'll send them out as well, so that you have these extra ones as well. And then just for anyone who hasn't seen my website yet, which is just my name and surname, jeanklopper.com, but certainly there's a whole, I try to put as much of the resources that I do make and are available is out there on my website. So if there's anything extra that you might be looking for, you might just find it there. So let's do randomness and some sampling. So I'm just going to run that first line of code, just what that is about now, and just to load the data tables, what that is. But the first question then really is, as always, and I suppose it's just all about making this almost into muscle memory. Of course, if I can type properly, so we're just importing NumPy as an NP, and we're importing pandas as PD. So there we go. And then we also have to import the stat module. So remember that is from SciPy, import one of its modules, which is the stats module. And we're going to use that throughout. And the rest, instead of having to type all of that, I just asked you to run this, but I have added this little extra one. I see quite a few people have watched the video on Matplotlib. So I'm certainly just going to use matplotlib here just for demonstration purposes, not for us to do any actual calculations. So I've imported it there, import matplotlib.py, the module inside of matplotlib. And we usually import that as that we see percent matplotlib inline. If you use any kind of Jupyter notebooks and you want the plots to appear below your code, that's the magic command for that. Now, there's something about randomness and patterns in having taken lots of samples or subjects and measuring some variable in them, that there's some pattern to those values, and we can refer to them as distributions. And in NumPy, fortunately, and in SciPy, which is built on top of NumPy or expands NumPy to some extent, there's a lot of named distributions. So some distributions occur very commonly, and it's nice to fit data to these, and they are named and we can work with them. And so the question there is use the inbuilt help function, and remember that's just a question mark, and what we are after is the random module. So I'm just going to say question mark numpy or np, which we're using the abbreviation .random. So that's a module. So on the right hand side, we're going to get lots of information about the module itself. So it's not a specific function, but if you do that and you scroll down, you see we get here to some univariate distributions. You see there the chi-square distribution, exponential distribution, the F distribution, that's for tomorrow, gamma geometric distribution, Laplace, logistic, log normal, all sorts of distributions there. And these are all available here in the random module. So if you say numpy.random dot any one of these distributions, and you can see NumPy carries quite a few, and I think SciPy is even more of these named distributions. So if you work in a world where you want to fit your data to a distribution, say, for instance, if we do maximum likelihood estimation, etc., all these distributions are out there for us, and we can also generate values from these distributions. So check out that module there by just using the question mark. And what I wanted here to show you, so we needn't worry about this code, but I'm just drawing random samples. You can see I'm drawing 1,000 samples every time from 3 different distributions. And so what I'm going to do is the normal distribution there. That's the normal bell-shaped curve, the log normal distribution. And for those of you who work in fields where the power law distribution is very useful, I'm going to show you the power law as well. So I'm just going to execute all this code, and I'm just using a bit of matplotlib just to show us. So what you'll see in the background, of course, is the histogram of our 1,000 values, the light blue, and then we see this estimate of that distribution. So we'll have the standard normal distribution here. It's a nice bell-shaped curve. Here you can see the log normal distribution, and here you see the power law distribution. So you can well imagine that you've collected data, and when you take a histogram of those, it sort of follows one of these patterns. So in many instances, we can fit our data to one of these distributions. So I just wanted to give you some idea just of 3 that we might use quite commonly, what they look like, but certainly for all of those that we've seen in the module, you can use this code. So as we said, we'll give you this, this notebook as well, so that you can start playing around with those. And then really, this is simple stuff, but I want to put it in here because I want everyone to clearly understand this, that in most cases in data science, there's a population and we do not have access to the whole population. There's no way for us to take a sample or consider some variable and go measure it in every subject in our population. In some instances it is. If we think about healthcare, there are some very rare diseases, extremely rare diseases, that there are only a couple of people in the world with that. And that population will be tiny. You might think of a very specific genetically modified animal or some grain or something, that there's just the whole population is quite small, and then you can investigate the whole population. But for most of us, the population is going to consist of millions, billions of subjects, whatever that is, from a chemical, some protein, all the way through to an organism, human beings, apparatus, doesn't matter what it is, there's a population, and we're going to draw from that population. So what I want to do here in the beginning and very clearly is we're going to simulate values for a single continuous numerical variable in a whole population. And we're just suggesting, because we are designers of this make-believe world, that in our population, there's only 2,000 subjects in our whole population. It doesn't matter what the population is, but on Earth, in the universe, in our galaxy or in the universe, there's only 2,000 of these. And that's our whole population. And since we are the designers of this, this make-believe world, for this specific continuous numerical variable, we say that that variable is normally distributed in this population. So we can say numpy.random.normal. So that's going to give us the normal distribution. And we can set the mean and the standard deviation for that distribution. Because if we look at this first one here, the normal, this is the standard normal distribution. It has a mean of 0 and a standard deviation of 1. But of course, we can move this left, right. So the mean goes negative, mean goes positive. And we can have that it's more squat, so lower, and the tails get bigger and bigger. So the standard deviation gets bigger. So that's under our control here. To the mean of 300 and a standard deviation of 50. And we want population, our population is 2,000 subjects. And we're using this numpy.random.seed. And we spoke about this seeding, the pseudo-random number generator, the algorithm that NumPy uses to generate random numbers. If we seed that algorithm with an integer values, and this time 42, what we are going to get back is exactly the same values. So if you run it and I run it, we get the same random values, and that makes the code reproducible. So I just want to spend a little bit of time there, depending on the field that you work in, but in many STEM fields, there has of late been, well, in some of them at least, this idea of a reproducibility crisis. People publish papers and no one can repeat the results. And that, of course, creates a lot of problems, specifically if the results of those reports are used in real life, because that was published and the results seem robust, we're going to change the way we do things. And, that might create problems. And then later on, someone else tries to reproduce those results and they can't. And then there's question marks. So there's this idea of the reproducibility crisis. And there's, of course, reasons for that. One reason, of course, would be just by chance, that there was some bias that crept in the selection of the subjects that went into the study. Most definitely that can happen, but we do have ways to mitigate against that bias, but still that can creep in. There's obviously confounding factors. In other words, there are some variables that determine the outcome, but we never measured them. And we don't even know that those, would play a role in the outcome. So the variables that we look at are actually just surrogates of something that is much more important, and they just, it's not our data. And so there's many more. The one that we're interested here in data science is the fact that depending on the software that you use and the code that you write, it is possible to make mistakes. And those mistakes can unfortunately sometimes be, let's call them mistakes that are made on purpose. Because certainly when it comes to statistical analysis, there are ways to analyze data. There are ways to decide on removing some of your subjects from your data set so that the results come out properly, and lots of things can happen. Also, I'm going to say, but this is just going to be me stretching, the truth a little bit, in as much as some of the commercial softwares, of course, you have no control over what happens behind the scenes in that commercial software, and it might be easy to do the sort of the wrong analysis there, or not understand what the coders of that commercial software meant by that piece of that button that you push to do get the results for you. And that would make your analysis, might make that make it so that it's not reproducible. And the whole idea behind Python, and R, Julia, these languages are open source. Anyone can see that. And the whole idea behind these notebooks are, and some publications are now requiring that you upload both your data and your code. And that's a brilliant, brilliant thing. If you can show the data that you collected, and of course, there are some instances that we can't because it might pertain to human beings, and there's all sorts of information about human beings that cannot be made public, but there are laws around all of these things as well. But if you can make your data available and your analysis, if you can show the Python code that you wrote, or the R code that you wrote, or the Julia code that you wrote, everyone can see how you did your analysis. And that sort of mitigates this idea of the reproducibility crisis. And I think that is one of the main ideas behind this openness of this community of data scientists, that we can show each other our work and everyone can see and then understand why you decided to do the analysis in the way that you did and how you came to your conclusions, because we can all read exactly what was done. And because if you delved into what this normal function does, you can look up online, you can find the actual code that went into there to generate these values. So we can all look at the internal structure, we can peer deeply inside, and we can all agree what happened here, which is a thing that is lost, of course, in commercial software. So really, I think that is one of the true both reasons for success and reasons, it's an exciting way forward that we mitigate some at least of the part of this reproducibility crisis. So that was a whole tangent, and it's my birthday, so I'm allowed. There we go. We've got this population, and because this is our make-believe world, we designed these 2,000 subjects. It's the only subjects of their kind in our make-believe world. And they have a continuous numerical, they have a variable, it's a continuous numerical variable, and we can go out and we measure that in each of the 2,000 individuals, so we know secretly what they are. But now a researcher comes along. This researcher doesn't know about all the values in the 2,000. This researcher has limited money, as we all do, and limited resources, human resources, collaborators, limitations in time, and all they can do is they can go at random and select 100 subjects from our population of 2,000. And that's how it works most of the time. We can go out and we can get, select, hopefully without bias, select these individual subjects from a larger population. So the code or the question asks, select a random sample of 100 values from the population. So by values, I mean the actual subject. So you would select whether that be in a test tube or an apparatus in a factory or some samples taken from the production lines, it doesn't matter. We can randomly select 100 of them, and we measure that variable in those 100 subjects. And I see here we're supposed to call it my sample, or so let's do my sample. And we've got to take 100 of those at random. So I think let's do this. Let's seed this so that if we all do the same, and I think random.seed. And so again, you will have the solution set already, but of course they don't have all these questions in. But for now, let's just make it 42. And so every time we run this code, we're going to get the same. So we'll do numpy.random, and one of the functions is the choice function, and that's going to allow us to choose some of these subjects in our population. And our population was called popvals, and we want 100, and we want 100 of those. And popvals, oh, I didn't run that line of code, of course, that cell of code. And there we go. So we now have, we're simulating this idea that we are researchers in the lab, and we can, we know the population out there, and we've selected 100 subjects, and we measure that variable in these 100 samples. But secretly behind the scenes, we know what the population looks like. But this researcher that we're simulating here, this researcher does not know all these values. This researcher will only know these 100 values now. And the next question was just create a pandas series object from your sample and use the describe method to show the sample statistics of your sample. So that'll be easy. Let's call it df, and we imported pandas, I think. So that'll be pandas.dataframe. And one of the easiest ways to generate a pandas data frame, remember that'll have columns, and the column will have a name for that variable. So it's to use a Python dictionary. So let's just call it var. And to that, we're going to attach my sample. So we're just creating a series object. We can still say data frame, and that should still generate that for us. And what we want to do is just to describe that. So df.var.describe. We've seen all these things before. And let's see. So there we go. We have 100 subjects, just as we thought. And for this specific continuous numerical variable, we see a mean of 302. And that, of course, is slightly different from, the 300 that we selected that when we designed our population. But of course, we won't know, this poor researcher won't know that it really is 300. They went out, this research team or researcher took 100 subjects, and this is all they know about this continuous numerical variable. They only know the data from their sample. So what we can do here, display histogram of the sample values and add appropriate title. So I think I put this in just so that we have a little bit of review. So I'll use Plot Express and just create a histogram. And on the x-axis, of course, we want my sample. Yeah, we can just do that. You can also use the data frame itself and then just refer to the var variable. You can do that. And let's put in a title. And the title, let's just say histogram of our values for our variable. And yeah, labels, I think on the x-axis, of course, it's just going to print out x now. So we can certainly change that. And we change that, of course, with a dictionary again. And let's just say something like variable values. There we go. And there we go. And one thing I want you to notice is our population was only 2,000, and that was taken from a normal distribution. So if we plotted that out, it's going to be a nice bell-shaped curve. And 100 out of a total population 2,000, that's quite a substantial proportion of the population for which we have data. So if we think about human beings, 7 billion human beings, 100 out of 7 billion, your distribution is not necessarily going to look the same as the distribution on the population, but 100 is quite a substantial fraction of 2,000. So this histogram showing us already the data, at least that we have, seems to be that we are going to have this normal distribution as well. But I want to just be clear that this is because 100, there's quite a large sample size if our population is only 2,000. And then I've just put this code in here that again, this notebook will be available to you. So what this does is it just shows this up, the difference between the population and the sample. And what I had to do here, of course, is just to make sure that the bins are equal and that we are representing this as probabilities here. So the height of these bars, if you sum them all the red ones and sum to 1, and all the blue ones, they'll sum to 1, just so that we get this idea. And we can clearly see, because our sample size is a substantial fraction of our population size, we sort of start seeing the same distribution in both of these. As I said, if your sample is a tiny fraction of the population, this is not always going to be the case. I just wanted to make that clear here. So calculate. The next one is calculate the mean and standard deviation parameters for the population. So remember, if it is something that we calculate from the whole population, we call that a parameter. And if that same thing that we calculate from a sample taken from the population, we call that a statistic. It's just the two definitions. So remember, that was pop vals. And so we want the mean from that. And what we want our pop vals .std, our standard deviation. And remember, I'm going to put here DDOF equals 0, but that is by default, it is set at 0, so we don't actually have to put it, because there's a slight different calculation that we use if we calculate the standard deviation of a population versus the standard deviation from a sample. It's slightly different. So let's just remind ourselves now, we set it, remember, we set it at pop vals, we took it from a distribution of 300. So we took 2,000 from this distribution. It's not going to, the mean's not going to be exactly 300. There's no ways to expect that. This is pseudo-random numbers. So just taken at random from this theoretical distribution. So it's if you take 2,000 samples from that, it's not exactly going to end up there. So let's have a look here. And so if we look at the mean of the population was 302 and the standard deviation was 49. So let's just compare this. So our researcher will not know this. So our researcher only has knowledge of these 100 subjects. So let's see what our researcher got. So it's my sample dot mean. And remember, we said my sample std for standard deviation, but now we have to say DDOF. And we set it at 1, the degrees of freedom is 1, seeing that we only have one sample of, so this is just one variable that we're looking at. And so let's see what this, it comes out to 302, 302.69 and 302.54. And I think what I want to do in this instance, I'm going to go back slightly and I'm just going to change, the seed a little bit. So let's go back because I want a bigger difference just to illustrate. And one easy way to do that, and of course, if you oh, I said actually there, seed the value to 1,200. I think I played around with this when I generated these because I wanted values that were slightly our population, so that our population, our sample looks slightly different from each other. So let's have a look. So there's our population still as 302 and 294. Okay, that looks better. So again, I changed the seed, so we're getting different pseudo-random numbers, but nothing else has changed in as much as there's still this idea that I have a population, and in actual fact, that variable value exists in each of these. The researcher doesn't know that. The researcher goes along, takes 100 subjects from our population and measures that variable, and so we'll only know those. And you can see that 100, the mean for this is only 294.98 versus the populations is 302. And you can well imagine this is a bit of a problem. Because in real life, this is all we're going to know. We're only going to know in data science, we're only going to know the values for this population. The statistics is all we're going to know. We do not know the parameter. And this is this idea of trying to understand what the probability was of finding 294, for instance. And so what we're going to do now is not necessarily what we'll do in real life, but this is all about understanding what is going on here. And what we do is, and we're going to certainly do that when it comes to the uncertainty, when we do bootstrap resampling properly, is that we're going to measure the uncertainty. And that's where we're going to measure confidence intervals around this mean, 294, lower bound and an upper bound. And we're going to think that the real population parameter is somewhere between those two bounds. But that's coming tomorrow. Here, we're just building the basic building blocks. So what are we to do in data science if we only know the values for our sample? That's all we know, but somehow we need for that to give us some idea of what the population really looks like, because that's what it's all about. We almost never, ever interested just in the results of our sample. They are a representation of a larger population, and it's that population that we're interested in. So one way we can do about it is by this idea of resampling. So what we're going to do is we're going to say that there we go. I just have to fix that little piece of code there. So this one is going to go out to. I'm not quite sure if this is in the in the original. But what we're going to do here is to say run the code tab below that generates 1,000 means from repeated sampling of the 100 subjects from the population. So what we're suggesting here is the idea that this researcher has enough money and enough time and enough collaborators, enough resources to do the study 1,000 times over. So next week, this person is going to go out and select 100 samples at random against this population and measure this statistical variable, the value for this variable, I should say continuous numerical variable, everyone, and calculate a mean for these new 100 subjects. Next week goes out again, selects 100 at random. So we're imagining that this is possible. So this is just at the moment going to come from the population. So we're going to generate this means underscore 1,000, and that's just an empty Python lib that we can use this method here. And that means every time this for loop runs, it's just going to append, and this is what English word means, append, just add to the end of all of these. So for I in range 1,000, temp mean is just going to be a random choice from the population of 100. And we just append to that the mean of these new 100 ones. So I'm doing exactly the same choosing as we did before, but I'm just putting that as a new variable called temp_mean, and I'm just appending that to this empty list. So when we do this for loop 1,000 times, we're going to end up with 1,000 of these means, a sampling mean. So we can also do, I think I just put this in because we can also do list comprehension. So let's just do this. I just want to show you, because eventually writing for loops like those, they actually become quite long. So let's call this means 100 alt. So if you were paying attention to something else, keep on paying attention to that. This is just a bit of extra. So it's numpy.mean. I'm still doing numpy.random, numpy.random.choice. And of course, I'm taking my choice from pop vals, the pop vals, and I'm doing 100 of those. And I'm saying for I in range, and we're doing that 1,000 times. So that's just the alternative way. It's called list comprehension. And of course, that is almost, depending on how big you write your for loops, this can just be a bit faster to do. Anyway, we've done that now. We've got this, we've done our study 100 times over. So when we're going to deal with just trying to understand our results as far as the populations are concerned, we can only resample from the samples that we have. So we're going to just want you to have that conceptualized difference between what we're doing here. This is just showing you that resampling is possible. And if our researcher went out again and again and again, every time they're going to get a different mean, what does that distribution of means look like? But when we do proper resampling, bootstrap resampling, it's only going to come from the actual samples that we have. So we'll get there. This is just this idea of building what are all the possible means that could be out there, because every time our researcher went out and they went out a day later or a week later or a week before at random, they should have different 100 subjects in their research. And we just want to build this idea of the one that you do when you do your research in data science, the one statistic that you have is just one of many possible that you could possibly have done, depending on the 100 subjects that you took at random. That's the whole idea here. So what is the mean of this sampling distribution of means? And that's exactly what it is. It's not a distribution of the actual values. It's a distribution of possible means if we could do the study many, many, many times over. So let's do that. numpy.mean is what we're going to do. And we're saying the means 1,000. So means 1,000. And let's have a look at that. And we see now it's 302. And what we can clearly see here is that this is much closer to what the population mean really was. Remember, we looked at what the population mean was, and in all those 2,000 subjects, and it was 302. And the mean of this sampling distribution of possible means. So very clearly, again, make that distinction. So we did our study 1,000 times over. Every time we selected 100 individuals, subjects from our population at random, calculated the mean, and we went out and did it again and again and again, 1,000. So you can start getting this idea that the value that we found, now what was the one that we found? 294, 294.98, so 295. That was just possible mean to find. And it is going to be our goal is to somehow express how likely it was or how probable it was to have found a value of 294 in amongst all the possible values that it could be. And this idea of this distribution of possible means, this mean that we found just doing our study once, because that's usually what we can do is do once, it is going to be a value that is very likely to occur should you be able to do the study over and over and over and over and over again, or it is going to be one of those means, or whatever statistic it is, that was very unlikely to occur. So certainly in this distribution of possible means, and we only did it 1,000 times here, this is a computer with enormous resources. You can do this 1,000,000 times over. Simulate having done this 1,000,000 times. It gives you this idea of how possible it was to have, it helps us to express somehow how likely or how probable it was this one. Because there is this whole this is going to be also a normal distribution or approximate a normal distribution. And some values, some means are going to be very likely to have been found, and some are going to be unlikely. So this is just the concept of it, and we're going to move on to the next exercise. I'll just say something about 8. There's no exercise that I wanted you to do there, so just a few things that I want to mention. And then in 9, we're going to put this into practice. The only difference is we're not going to know what the population looks like. This here we did, and we can get this idea that if we do this over and over and over again from the population, it does look like this distribution, the mean of all these means, is very close to what the population actually looks like, because the mean in our population was really, for this continuous numerical variable, was really 302. And we're going to build on this idea of resampling, not from the population, but only from the sample that we have. And that brings us to this idea of hypothesis testing. So I really want you to read this or play with this notebook or watch the video lecture, because this is really the crux of the matter. And this is this idea of the scientific method depends on hypothesis testing. That no matter what field you are in, a question might arise in your head, which you have to turn into a research question. And whether that be business oriented or manufacturing oriented or scientifically oriented or healthcare oriented or biology, or it doesn't matter what it is, this research question pops up. And you have to be able to express that almost, I want to say almost as an alternative hypothesis, because your null hypothesis, before you collect data, before you know the answer, always has to be the base value. And that is the scientific method. In science, we won't believe anything, and we accept, we believe at the moment without there being any data that our hypothesis basically does not exist or is not so. If I can use that term, it's not properly expressed. So a common null hypothesis is if we're just comparing means to each other for two groups, that there's no difference in the means. That's going to be our null hypothesis. But we might be very interested to think, if I can use an example from healthcare, that there's a new drug on the market, and we believe that this new drug is really going to lower blood pressure. So we're going to have these two groups, and some get a placebo. That means there's nothing in the medication that they get, a little sugar tablet, and some get the actual tablet, and then we measure the blood pressure afterwards. And our null hypothesis would be that there's going to be no difference in the change of their blood pressures. That's our statistic that we're after. We're going to say there's going to be no difference. Our alternative hypothesis then is, yes, there is going to be a difference. And we're going to collect data. We're going to set a very arbitrary alpha value. And if you've read the notes or watched the lecture, you know that an alpha value is a very arbitrary thing, usually 0.05. In high energy physics, that will be a much, much smaller value. We just set this value by which we would suggest that if we cross that threshold, that we reject that null hypothesis and only then accept the alternative hypothesis. But I think, please watch the lecture, please read this. In statistical analysis, we don't actually prove this. All of what we're doing is we're basing it on the fact that in reality, without us knowing, the null hypothesis is actually true. Given that that is so, absolutely so, there's this whole range of possible values that we could find, and the one that we find will be either very common or it will be very rare. And if it crosses this threshold of rarity, we say, oh, we have evidence, we reject the null hypothesis, and now we accept the alternative hypothesis. So let's look at that idea here in 9. So if everyone is open that one, we just asked to run these first cells. Let's run them and load the table. Import NumPy and Pandas. So let's quickly do that. Import NumPy as NP. Import Pandas as PD. So we've got those. Is that what we asked? Yes. And then also from SciPy, we're going to import stats module. So let's do that as well. Then I just said run this code. Of course, that's just going to give us our plotting. And so what we're generating here at the moment is we run the code cell below to generate two values I should actually set there for two variables. So we're going to seed the pseudo random number generator to I've put there 28, and then we're going to generate random values for these two variables. Height and group is what we've called them. So these would be computer variables, height and group. and we assign to that the following. So to height, we assign 200 values. So in our study, so what we're trying to simulate here is, in our study that we're doing here, there are 200 subjects, and we're measuring their height. And their height is from what we call a uniform distribution. So a uniform distribution is very easy to conceptualize and visualize in your mind. It's just that every value in this interval, and we can see the interval goes from 150 to 200. So it's integers, so 150, 151, 152, 153, etc., until 199. Remember, Python won't include that 200. Every value there is equally likely to be chosen at random. So if we were to visualize this as just a straight line, there's no bell-shaped curve to it. There's no some values are more likely to occur than other values. Every value is an equal likelihood of being chosen, or probability of being chosen here. So this is certainly not a normal distribution. Our continuous numerical variable in our study is definitely not normally distributed. It's a uniform distribution. And then we're going to use the choice, and we're going to choose 2 strings, Roman numeral 1, Roman numeral 2, and also 1,000 of those. But this one you perhaps have not seen. P equals a probability, and you've got to have as many probabilities there as what you have in your Python list there. So we're saying it's 60% likely every time that you run this over the 200 times to choose a 1, and only 40% likely that you'll choose a 2. So there'll be a bit of class imbalance there, more 1s than 2 on that. And then in the code cell below, we're just putting that in a data frame, and we're just printing the first 3 lines. Remember, with head, if you put nothing there, it's going to print 5, but you can actually put a value there of how many you want to see. So there the first 5 groups was 1, and there's our heights. So let's think about this study. We know nothing about the population from which these 200 subjects were taken. We don't know the population at all. All we know is these results. We are now the researcher, and we have no idea of the rate of population. But the results that we find from these 200 subjects for these 2 groups is what we're going to use to infer. We're going to infer these results to the larger population. And that might have tangible meaning. It might mean something that someone has to go out and do, manage individuals from that population based on these results. So inferring these results to the larger population. And what we're just simulating here is that somehow these are in 2 groups, and those 2 groups might mean anything. And I'm just using height there just as, some variable name. It might, consider it anything else. But we have these 2 groups, and the way that we make these groups is purely by one of our columns, one of our categorical variables. We divide up our data set by the sample space elements in that categorical variable. So we'll have subjects in group 1 and subjects in group 2, and the way that they divide it is just whether they get a 1 or a 2, Roman numeral 1 or 2 in this group. And that's when we say we compare groups with each other. We are here, in this instance, comparing a continuous numerical variable, that very same variable, in each subjects in each of the 2 groups. So that's a comparison of a continuous numerical variable between 2 sample space elements of a categorical variable. So the division is by the sample space elements of a categorical variable. Tomorrow we'll look at correlation, for instance. And that is a continuous numerical variable against another continuous numerical variable. Here it is the same continuous numerical variable by 2 groups. And of course, one easy way would be to compare the 2 means to each other. What is the difference in means between these? So in the next section here, then it is asked, calculate the frequency of the sample space elements. So we set it at 60/40. So let's see, what it really turned out to be, because that's always important to do. The value counts. And we see it came out at 127 versus 73. So there's certainly a bit of a class imbalance here. And that's very normal, that you go out and you do some research, and the 2 groups that you form are not equally sized. If you do something like a randomized controlled trial, of course, you can aim for that to be equal, but it really isn't. And I think, this was just some exercise, show this as proportions. I'll cheat a little bit, and I'll do a copy and paste of my previous code there, because this is just, remember, normalize equals true. And if we set that, we get a proportion. So let's just see it. We asked for 60/40 split. We got about 63.5 and a 36.5 split there. So calculate the summary statistics for the height of the subjects in your study. So let's have a look. So it's df dot, is it df dot height? Yes, we had. And then dot describe. I think that's what we asked for. I might have to change that question a little bit because we've already created the, oh yeah, the hint was, remember that, just to remind you that this is a series object, so df.height, so we're only looking at that one column, and we just want to describe. There's 200, we have a mean of 173, and that's for all of the individuals combined. So let's just group them, and that's the next question. So that's going to be df.group by, and we're going to group by the group, so those two sample space elements, and then from that we want the height, and there's no illegal character, so I can just say dot height, and we do a dot describe, because now it becomes interesting. We can see that we have a mean of 173 in group 1 and a mean of 174.56 in group 2, and there'll be a difference between those two means, and I think that's exactly what the next question is. The statistic of the study is the difference in means. So that's our statistic. And somehow have got to understand this difference. So let's just run, remember the way to do that, df.log, and then rows, comma, columns, or just the rows and then dot, the column dot height. So that, remember, I showed you there are different ways to do this. I'm saving that as the computer variable stat, just to be clear, as our test statistic here is a difference in mean. And if I order of subtraction the other way around, it would be positive 1.37266. But here it's negative just because the height in the first group was than the height in the second. But that's a very important stand. The order of the subtraction is going to give you a negative and a positive sign here in front. So because our null hypothesis is that there's no difference, alternative hypothesis, there is a difference. And that means it doesn't mean if that matter if the difference is negative or the difference is positive. We've got to view both of them. And in the lecture, you'll see me or read about the fact that that's a two-tailed hypothesis. Now, once again, I'm just going to reiterate. I'm going to sound like I'm just repeating myself, but it's very important, the fact that this is all the information we have. We do not know what it looks like in the larger population from which these 200 subjects were taken. And we're going to do the same thing is we're going to resample. But now I want you to think about this scientific method, about the null hypothesis. Under null hypothesis, there's no difference between the means in these two groups. And if you think about it clearly, you would have seen it in the notes, seen it in the video lecture, is under the null hypothesis, we can randomly reassign individuals to either of the two groups, because we said it doesn't matter. The means for these two, this continuous numerical variable in these two groups are exactly the same. That's our null hypothesis. Under that hypothesis, we can randomly reassign people to a new group. And that's exactly what we remember. Once again, this is only from these 200 subjects. We know nothing about the population. So the way that the code here goes, and I didn't ask you to write it, it's just all here. So I'm going to create this empty Python list called mean_stat. And I'm just warning you with NumPy specifically, but with pandas as well, if you start doing some sort of reordering, so changing the sorting, it gets done to the original, and then you sort of kind of lost, you've messed up your original data, which you won't do. So it's a very good thing always just to make a copy of your data. So I'm saying this time height.copy. And remember, that's all 200 heights. So it doesn't matter what group they are in. I'm just making a copy of that, and I'm assigning that to a new computer variable, height_copy. So now I'm just going to change height.copy. I'm not doing anything to the original. So I don't want to mess up the original. That's the data we collected. I just want it to live in peace. And this time we're not using list comprehension. I'm just using an ordinary for loop. So I'm doing it 1,000 times over. And I'm going to say numpy.random.shuffle height copy. So remember, they were all in order from 1 to 200, somewhere in 1, somewhere in group 2, group 1, group 2, group 1, group 2, which we've seen here from the data frame, in 1, somewhere in 2. So I'm just taking that whole list, and now I'm just reshuffling it. I'm just shuffling it. So the order is now completely rearranged. And because we had this, when we did this to look at how many there were, 127 in the 123 in the other group, remember that they are now in completely different order. So because they're in different order, I'm going to say these first 127, so this high.copy, the first 127, and then from 128 till the end, those would be my two new groups though. So making them the same sizes as what my exact study turned out to have. So we looked at those value counts. We know exactly what size they were. So we're doing that here. So in this reshuffled copy, we're putting some of them now, 127 of them in group 1, and this new group 1 and the new group 2. And we do that over and over again. So every time it gets reshuffled, and that is what we're trying to simulate here. We are randomly reassigning subjects to group 1 and group 2 every time. And we're subtracting those two means from each other, and we are appending it to this empty list. So in the end, we're going to have a sampling distribution of our test statistic, which is the difference in means in this instance. So let's go. We now have all of this. And then the next code, I just asked you to do a histogram of that. So px.histogram, and there you can see the differences in means. Now, if you think about it, our variable that we simulated here was from a uniform distribution initially. I just said, there we go, rand int between 150 and 200, every value was as likely as any other value. It was not bell-shaped curve. It was not taken from a normal distribution. It was taken from a uniform distribution, a straight line. And look at this. And there's a law for this, what is happening here. So the sampling distribution of possible test statistics here approximates this normal distribution. And it's around a mean of 0. And as it gets away from 0, this difference in possible means, and remember, this only came from these 200 subjects that we have. We don't know what the population looks like. And we just, under the null hypothesis, randomly reassigned our subjects, our individuals, and we did it 1,000 times over, and we just did the difference in means every time we did this over 1,000 times. And what that does is it simulates this idea of what differences are very likely to have occurred, and under the null hypothesis, of course, it's got to be no difference between the two. And as the difference gets bigger and bigger and bigger, either on the negative side or positive side of 0, because, again, it depends which order I subtracted the two means from each other. And remember, ours was negative 1.37. So negative 1.37 is somewhere, negative 1.37 somewhere out here, but I've got to look at the positive side as well. So this gives us an idea of where our one study that we did, where did it fall on all these possible 1,000 resample possible test statistics it could be? Was it very likely to occur? Not likely to occur. And one way in data science to extract meaning from this, or to explain what was going on, or how probable it was to find that, is to use the concept of percentiles. So when we looked at the measures of dispersion, we spoke about percentiles or the quartiles. Percentiles is just each individual percentage. So we can look at the extremes. So we can say what fraction of these possible test statistics, if we could do this many times over, was less than the negative one. And we just take the absolute value for what fraction was more than. And we just have to look at the alpha value. And the alpha value that we set here for ourselves would be 5%. That would be common, 0.05. So we kind of need to know what proportion of this test statistic. I'm going ahead of myself. When we talk about uncertainty, we're certainly going to use that idea of this, the idea of 95% of this area. So I'm running ahead of myself. That's what we do there. Yeah, though, all we want to know is what fraction of the values was less than our test statistic. So our test statistic and less extreme, so on this negative side, and positive 1.7 to the positive side. So what fraction of all of these possible ones was our value and more extreme? And that's what we get asked to do here. So what we need to do is, let's just do numpy.sum. So we just want to sum up how many true and falses we have. So we're going to use a conditional. So we're just going to turn, one thing you'll have to do is to turn, we have a Python list at the moment. So let's just turn it into a Python array. So numpy.stat, and you'll see that in the lecture, numpy.stat. Numpy.array mean.stat. So we're just turning it into an array, and we're saying less than our stat. Now remember, our stat was our difference from our one study. What was that difference in means? So what this condition is going to do, it's going to run over all these resamples. We did all 1,000 of them, and it's going to return either true or false. Going through all 1,000 of them, was it less than the stat? Going to return a true, and internally Python represents that as a 1 and false as a 0. So if I sum over all of these, it's going to sum up all the trues. So in effect, what I'm getting here is how many of these were less than. I'm just summing up how many was less than of all these possible 1,000 ones, how many was less than my statistic. And remember, I want to express this as a fraction of all of them, and there was 1,000 of them. So I'm just saying how many of those were less than our negative. So let's run that. So very clearly, I want you to understand our negative was, I think, negative 1.73 out here. So I'm saying what fraction of this was less than, of all of these 1,000 possible ones, what fraction was less than. And I'm also wanting to know what fraction was more than the positive one of that. So I'm just going to copy that, and we want that was more than, and I've got to put a minus there because minus times minus is positive. Now just be careful, if your test statistic turned out positive, then of course you've got to put the minus sign there to make it the negative, but in our instance, our test statistic was a negative. So here, a negative times a negative is a positive, so we're actually talking about 1.73 there, and we divide it by 1,000, and that gives us an area of about 2.62. And if we add those to each other, so let's add this one plus that one, add those to each other, and that gives us this idea of how likely it was, how probable it was to have found this difference. So we only do that study once. We found a difference 173 for the mean in one group, 174 in the other group. And that gives us a difference of minus 1.37, sorry, not 1.7, minus 1.37 or positive 1.37. We then resample, under the null hypothesis, we randomly reassign these individuals, because once again, our null hypothesis states that there should be no difference in these means. That gives us this distribution of possible values, a sampling distribution, we call it. And then our result fell somewhere on this, on all of these. And we're using here the method of percentiles, as I say, because we just want to know what fraction was less than our statistic and more than our statistic on the positive side. We add all of those, and we can say that there was this probability of 0.513, a 50% probability of having found this result that we found, or more extreme. And we're only basing that on the null hypothesis in our actual data. And we infer these results now to the population. And if our cutoff was alpha of 0.05, that 0.5 is more than 0.05. So we failed to reject the null hypothesis, and we still sat with that initial null hypothesis that there is no difference in between these two groups. So this is the way of using resampling to estimate how likely it was to have found your result. And it's a very powerful way to go. So what I've put in here for you is just the statistics way of doing it, just using a statistical test. And the most common test that we'll do here is student's t-test. Now, if you don't know the story of student, it's for me absolutely a nice story, a fascinating story. Of course, student wasn't his real name. Maybe I'll ask or maybe I said it in the lectures, I can't remember. But maybe someone can pop up what his real name was. He worked for the Guinness Brewing Company, and they didn't want their secrets out, and he still wanted to publish his results, and they gave him gave him consent to publish his results under pseudonym, and he chose student. And so we have student's t-test, and the t distribution itself, remember, that's also a sampling distribution that looks very much like the normal distribution, but it's also a sampling distribution, and it's only based on the number of groups we have, in our instance 2 groups, and or at least then the number of samples, I should say, the number of samples in our study, and that's number of samples determines what this distribution actually looks like. And if the number of samples in your study gets bigger and bigger, the t distribution starts to look very much like the normal distribution. So students t-test is used to look at or express this idea of the probability difference. Our test statistic is the difference in means. And in the stats module, you'll get all the statistical tests, many of them. This one, t-test underscore IND, is t-test for independent groups. So those two groups can't be dependent on each other. Dependent groups might be measuring this variable before and after some intervention. So every, the two sets of values would refer to the same individuals, measuring them twice, or something like homozygotic twins, for instance. Those things will not be, the values there won't be independent. But here we have just commonly independent groups from each other, and I pass these two sets of heights. And what we're going to get back is a t-statistic. And I might make a video if you want to for me after the fact, how does this actually work? How does the student's t-test actually work? So, these are calculations, there's equations, there's a calculation, you do that calculation and you end up with that p-value, 0.51. And that is very close, 0.513, so 0.514, very close to the simulation that we did. And that's this whole idea of this resampling. It is an approximation to some extent of using these statistical tests. So not an easy concept to get your head around with the first time, but the whole idea behind all of this is that when you do some analysis in data science, you're going to find a result and somehow want to infer that to a larger population. And you've got to express somehow how probable it was for you to have found the results that you found. And this idea of the very powerful idea, and it helps us to express this probability of having found our result. And if we use this idea of hypothesis testing, it allows us then to decide whether this research question we had, which is stated basically as the alternative hypothesis, whether we can reject the null hypothesis and accept the alternative hypothesis. And depending on the research that you are then doing, you've actually proven your hypothesis. You had this research question and you thought that this was so, and you went out, you collected the data, and the result that you found was very unlikely to have been found given the null hypothesis, and you accept that alternative hypothesis, and that would be a successful result. Although we also know today in this reproducibility crisis, we don't see enough negative results. So that we would call not, failing to reject our null hypothesis, some would refer to that as as some kind of failure. But that's just as important to know as the situation where you do reject your null hypothesis, finding these unlikely results. Both of those things carry importance. And sometimes people won't publish their results if they fail to reject their null hypothesis, or a journal might not accept that paper for a variety of reasons. I think that happens less and less now, but it's very important to publish and make known these results where you fail to reject the null hypothesis. Otherwise, there's this bias in the literature of only the positive results. And it sort of puts extra emphasis on those positive results, but those very in derogatory terms, the negative results, they should also be known. It's very important. So I promised a little extra section here, and I just want us to think about what we did here. We went ahead and we just did students' t-test. And I think someone right before 2 o'clock was asking, what can you set a difference that's not 0? Yes, of course you can do that. And if you just use the students' independent t-test and you looked at all the arguments that you can set there, you'll see very easily, how to do that. But we'll put that in our list of extra videos to make after this week, because we're getting into deeper things here. And this is the basics in this first week. But I want you, I hope for some of you at least, and I remember when the first time, I read about this in a textbook, studying this, and this idea opening up of understanding. So this, what you see is basically p-value, understanding what that meant. It's this expression of your results, the probability of having found your results, and how that relates to the larger population from which you had taken samples. And someone spoke about the different distributions. Of course, I've shown you a couple there, and you can use that in a question mark np.random, and you can look at all those distributions, look at SciPy. So when you Google SciPy, distributions. You'll see a bunch of distributions, and depending on the kind of work you do in data science, you might want to fit your data to one of those distributions. That's an important aspect, might be an important aspect of your work. And then these tests. Now, tests that depend on a distribution. And in this instance, our test did actually depend on a distribution, because it was very important that this sampling distribution had a normal distribution. If it did not, then we'd have to have a different approach. Or if you wanted to just use statistical tests like students' t-test here, that depends on a distribution. It depends on a t-distribution, and every distribution has parameters. A normal distribution has two parameters, a mean and a standard deviation. A t-distribution only has one parameter. So all of those distributions will have certain parameters. So when we use tests that depend on those parameters, we call these parametric tests. So certainly most of you would have heard of students' t-test. That is a parametric test. And if we have parametric tests, it might also mean that you might guess that, yes, we do have non-parametric tests. So when do we use parametric tests and when do we use non-parametric tests? And that's just a little bonus piece I wanted to throw in there for those that are interested. There's actually this world in between the two, because if your data is not normally distributed, you can transform your data. So one of the common ones is to do a log transform. Just take the logarithm of each of your values, or take the square root of each of your values. Of course, there's problems if your values are negative, but you can transform your data, and sometimes then it'll act better and be more normally distributed. The modern emphasis really, and I won't call it modern emphasis today, the emphasis really is on rather using non-parametric tests. So if you're going to go for a student's t-test, you're going to go for analysis of variance, anything that depends on parameters or these name distributions, parametric tests, that data must meet certain assumptions before you can use those tests. And I think that's one very powerful thing that you can do if you pick up a research paper now and you look at the methods section of a technical paper and look at the methods section, if they do describe, when did they use parametric tests and when not, because that's a very easy mistake to make in the beginning, is that you use these parametric tests and your data does not meet the assumptions for the use of those tests. That's horrible. So I just wanted to mention right here, because it's very easy to test two of the main assumptions for the use of parametric tests. And I'm doing that specifically here for continuous numerical variables. And the two main ones, there are more, definitely there are more. The two main ones I want to mention again is this normality and outliers. So what we really mean by normality is we don't really, our data, the actual data, our values, not the sampling distribution of it or anything, the actual values for that numerical variable has to be somewhat normally distributed. What you're actually referring to in this instance is that the variable in the population is normally distributed. So that's what we're really referring to now. The problem that we do sit with is the fact, obviously, that we don't know what the values look like in the whole population. We only know what it looks like in our little sample. And sometimes our little sample is going to show a distribution for that variable that doesn't really look like the population looks like. And that is one of the reasons why I always go for the biggest sample sizes you can get. The closer the sample size is to the population size, the better your results are going to be. But in many instances, it's going to be a tiny fraction, but that's all we have to work with. So what I'm quickly going to show you here is what I like to do is just to extract the values that I'm interested in. So I'm going to create a different group 1 and a different group 2. So I'm going to use df.loc and then df.group. This just makes it easier. So forgive my slow typing just for a little bit. And what we want from that, of course, is the height. And so let me just copy and paste all of that. And I'm going to make group 2. And that's going to be group 2. So you can clearly see what I'm doing here. I'm creating 2 new data frames. One will only contain group 1 subjects in it, and one will only contain group 2. So I've got these individual ones to work with. Okay, I'm going to use that a little bit later. So let's just talk about how can we decide whether what this distribution looks like in these 2 groups, and how can we sort of infer what we think it looks like in the population out there to try and make sure that this variable that we're dealing with is normally distributed in the larger population. And one way for us to do is just to look at the distribution of the actual values that we have. Let's see what that histogram looks like. So let's just do a histogram. So px.histogram, lowercase because we're using Plotly Express. And so it comes from our data frame. And on the x-axis, we want our height. Let's put height there. And of course, we want the color to be our group. So what that color means is not the actual color, red or blue. Of course, it's going to come out red and blue, but it just means show me a histogram for each of the sample space elements in that group. Let's put a marginal in there. And I'm going to do little box plots in the margin, because that gives us the same idea. Remember, you can look at distributions both with a histogram and a box plot. A box plot's kind of worse because it's more about the quartiles than anything else. But let's just give it a little title as well. Let's just say, what can we say? Let's just say the heights. Doesn't matter. Let's have a quick look at this. So there we go. So clearly from here, I mean, we can get a bit more granularity by making the bin sizes a bit smaller. But we can see here from this histogram that it doesn't really scream out to us that this is a bell-shaped curve for heights in both group 1 and group 2. It really doesn't. And then, by the way, the margin, there's our box and whisker plot in the margin there. It doesn't really, shout at us that this is a bell-shaped curve. It doesn't really look like our data, our actual data is normally distributed. Of course, as I said, what we're really interested in, was it taken from a population in which that variable was normally distributed. So for those that have watched the video on matplotlib, I'm just going to use matplotlib.pyplot as PLT, because it has it allows us just to create the following plot that I want you to be aware of. It's a very nice plot. And it comes from SciPy stats library, but the stats library is actually going to use matplotlib to draw the plot. So you have to import that. Stats.probplot, a probability plot. So all I want to look at here now, let's just look at group 1. So that is just going to be the heights just for that group. The distribution I'm going to look at is a normal distribution. So I'm comparing it to a normal distribution. And the plot must be a matplotlib plot. Oops, what did we have here? Let's just see who can find my my mistake, my comma there. There we go. Here's my comma. I was quick enough for that one. So this is called the quantile plot, QQ plot. And I've set the distribution to be the normal. So that's what the norm is. And that's the red line that you see there. And it's the theoretical quantiles against the ordered values on the x-axis, theoretical quantiles on the x-axis, on the y-axis, the ordered values. So it's a bit of an explanation as to what that is. And we can certainly make a video about that. What I want you to see here is that red line is a normal distribution. And you can clearly see our values. Those are the blue dots for the heights in group 1. They don't follow that red line at all. They snake all over the show. That is a visual indication that our data is not from a population in which that variable is normally distributed. If it was, those blue dots, our actual values from group 1, the heights of group 1, would be along, they very closely hug on top of that red line. And that's a QQ plot, and that's a very nice, quick visual indication of whether we are meeting this assumption of normality. And we very clearly, according to, for me on this plot, we're not meeting this assumption. And remember, we also cheated a bit because this wasn't data from actual individuals. We simulated that and we took it from a uniform distribution. We didn't take it from a normal distribution. So it was never going to be normally distributed. So that was a bit of a cheat. But I want to show you here that at least according to this plot, we're not meeting this assumption of normality. So let me copy and paste that down here, and let's go for group number 2. For group number 2, and lo and behold, it looks just as bad. it does not follow this red line. And I've indicated that I want a normal distribution. So I'm doing my QQ plot here just to measure against or visualize against the normal distribution. So we've looked at two ways now. We've seen our data is not really, our actual data value doesn't really look like it's normally distributed. We've done the QQ plots now, another visual way just to see whether, we meet this assumption of normality. And definitely it doesn't look like it. And there are actual statistical tests you can do. And you use different tests, and they've got their pros and cons and certain situations in which you use them and those don't use them. One is the Kolmogorov-Smirnov test, and the other one is the Shapiro-Wilk test. So let's look at the Shapiro-Wilk test. So that's stats.shapiro. There we go. So the null hypothesis of the Shapiro test is that you can see there, Shapiro test for the null hypothesis that the data was drawn from a normal distribution. So if our alpha value is 0.05, if we get any value over 0.05, we fail to reject this null hypothesis, which means that it is from a normal distribution. So let's put in group 1 now. Group 1, all the heights there. And what it gives us back is our Shapiro-Wilk test statistic as the first value, and the second value is our p-value. And you can see there 5.6 times 10 to the power -5, so 0.00005 or 6. That's that's much smaller. So we reject our hypothesis. And the alternative hypothesis is that no, this is not from a normal distribution. So that's a statistical test. So we've seen visual tests. Now we see statistical tests. Let's run this. Let's run this on group 2 as well. And let's see. In group 2, and we should find another 0.00259. So that's still less than 0.05 if that was our alpha value. And we reject the null hypothesis of the Shapiro-Wilk test. And therefore we say that this data is not from a population in which this continuous numerical variable is normally distributed. So we have a bit of a problem here. We cannot use students' t-test if you were just going to use a statistical test to compare the heights in these two groups to each other. And by that instance, either you have to transform this data, or perhaps arguably better is to use a non-parametric test. So that's one way. So look at these QQ plots, do the Shapiro-Wilk test or one of the other tests that you can read up on and how to do these. The other way to go about that is just to, that would be for normality. So the visual test and the statistical test. The other main assumption that I want us to look at just here, just for this course, is just if there are too many outliers. If there are too many statistical outliers, and there isn't an exact hard and fast rule, but if there are too many, and so I put those too many in quotation marks, I'm just talking in general terms. If there are too many statistical outliers, then you've also got to be slightly concerned about using parametric tests. And again, there is 2 ways to go about it. So let's do a visual test. And one is just to create box and whisker plots. So let's create one quickly, go.figure. So I'm going to use graph objects there. So I've got fig there, and I'm going to add a trace. And to that trace, let's make it a go.box because it's a box plot. And for the box plot on the y-axis, we're going to put group 1. And if I want to do more of them, I better name them. So Plotly will put them, or put nice legends to those. So 1, and let's also do the box points. I think, yeah, let's do the box points all. So let me just do this one first. Let's make it outliers. Outliers, there we go. So I'm just doing the 1 at the moment, so only for group 1. So remember what a box and whisker plot is. The box in the middle, the lower edge of that box, you can see there's Q1, quartile 1, that's 160. That means if we put all the heights in order, that a quarter of them will be less than 160. The middle one here is the median, which is just the second quartile. So the median is 174. Half of the values will be less than 174. Third quartile, 3/4 of the value will be less than. And then we have these little whiskers at the end. And at the moment, it's showing the min was 150 and the max was 198 because there are no statistical outliers. So by the way, if I put box points all, I'm just going to show you all. it just does this nice jitter of, jitter means it moves them left and right so they don't all sit on top of each other. But it just shows you all our data points, and we can see none of them, the highest one was 198, the lowest one here was 150. And so none of them are suspected outliers. If they were outliers, some of these will be beyond this whisker, because this whisker will no longer identify the maximum and the minimum. It will be 1.5 times the interquartile range, which you'll remember is the difference between the third quartile. So that 185.75 minus the 160 of the first quartile. You multiply that difference by 1.5, and you add that difference to the third quartile. That'll give you the whisker at the top. And anything beyond that will now, there'll be dots here, that'll be an outlier, a suspected outlier. And the same thing subtracted from the first quartile value. And so this bottom whisker will then denote that limit, and if there were any of these dots, the values below that, they'll appear here. So we'll see statistical outliers. And in this instance, neither of them have statistical outliers. The better way, or perhaps another way that I just want to show you to go about that, is to use a mathematical equation. So I'm just going to do some LaTeX code here. So let's do frac and two of those. So it's going to be a fraction, a numerator and denominator. Let's make x sub I and minus bar of x, puts a bar over the x. And here we want a sigma and subscript x. Oops. Let's see. There we go. So this is what is meant by standardizing your values. So at the moment, the heights will have a value 158, 161, 178. And all you do is you take each of those values and you subtract from it the mean for that variable and divide by the standard deviation for that variable. And that way, every value is now not the value anymore, but it is expressed in units of standard deviation. So how many standard deviations is that value away from the mean? And what we can do now, let's do that programmatically. So I'm going to say, let's start with group 1. So that's all the heights in group 1 minus group 1 dot mean. So I'm subtracting each of those, each value. I'm subtracting the mean from each of those. And now I want to divide it by the standard deviation. So let's do that. Actually, I'm going to put it in here because I've got an extra set there. So I'm going to divide by group 1 dot standard deviation, STD, open close parentheses. And so that's going to give me all of those. But what I want to do is I want to sort the values. And let's hope I didn't make a mistake there. There we go. So I'm expressing every value as a standard deviation here. How many standard deviations from the mean there are, and I'm sorting the values from the most negative to the most positive one. So we don't see the actual heights anymore. We're seeing them expressed as units of standard deviation. And what you don't want to see is, again, it's a rule of thumb. You don't want to see too many that are more than negative standard deviation away and more than positive 3 standard deviations away. We can see the one was minus 1.65 standard deviations away, and the most positive one was 1.6. So that's certainly not beyond -3 and beyond +3. So visually, we didn't have any suspected outliers, and just numerically, we didn't have any suspected outliers. So once again, just do the express them each value as units of standard deviation, and what you want is not values many values less than -3 and many values more than 3. Just a little sort of rule of thumb. So what you do then, what we've seen here, and you can do the same for group 2, you're going to see that there really aren't any. So what would be we've seen here now, we're failing to meet assumptions for the use of a parametric test in this instance. So we can't just use students t-test if you're going for those. So we can't use a test that depends on some parameter, some specific name distribution. So we'll have to use an alternative. Those alternatives are non-parametric. Non-parametric alternative to students to t-test is a test that goes by many names. Usually it's called the Mann-Whitney-U test. And of course, you don't have to worry. SciPy and Python is going to have that. So it's stats.Mann-Whitney-U, and there it comes up, Mann-Whitney-U. And what we're going to pass is this group 1. our values in group 1, our values in group 2, so those two different heights. And then we've just got to put that alternative, as you can see there in the tooltip that pops up, because we, most of the time in the lecture, I explained when to use a one-sided alternative hypothesis. Most of the time we want a two-sided alternative hypothesis, so we just put that because I think that's not the default. And let's look at Mann-Whitney U. And we get a p-value now, a test statistic, a U statistic, and we get a p-value 0.503. And that's, if you think about it, very, very close to the p-value we got from using a parametric test. Because I don't want to understate, or I want to mention that many times these parametric tests, like student t-tests, are actually quite robust. They can take a bit of a knock. You know, you can cheat on the assumptions a little bit and they won't go, you know, they won't fall apart. But I want to be clear here that if you want to use these statistical tests to compare your, you know, different values, make sure that they meet your data meets the assumptions for the use of that test. And in broad terms, we can classify them as parametric and non-parametric. And there are more assumptions than just the two that I've shown you, but those are certainly are the two very important ones, specifically if your data is from a population in which that variable was normally distributed. Do those QQ plots, do the Shapiro-Wilk test, Kolmogorov-Smirnov test, read up on when to use those. And if your data fails those assumptions, either transform the data, which I really don't often do, rather use the non-parametric tests. As you can see here, for instance, if we compare more than two groups to each other, we'll use analysis of variance, ANOVA, and we'll also test the assumptions then, and the alternative to that would be the Kruskal-Wallis test. So for many of these parametric tests, they are non-parametric alternatives. Now, these non-parametric tests, they also have a few assumptions, but they're also very robust against those assumptions. But it's certainly just, I just want to leave you with that, some thoughts and ideas for future exploration. But one thing about data science that I think I should mention very clearly while I still have all of you is the fact that we have to be robust in our analysis. So for many of us, many in data science, many people in data science are not formally trained, you know, don't have a PhD in statistics. But that does not mean we can let go of the rigor of statistics when we use these tests, that we should still aim to be very rigorous with these things. So I really want to underscore this idea of, you know, read up on these things, look at the assumptions for the use of the tests that you are going to use, or perhaps you've used them before and you haven't clearly looked at those assumptions. Clearly, you know, look at those assumptions, test them thoroughly, and, you know, choose an appropriate test. And then once again, in this world of open data analysis, where we want to get rid of this reproducibility crisis, when you put the results out there like this, everyone can see what the steps were you went through to, you know, and it builds the veracity in your results. So that was what today was all about, seeing the results that you get in a broader picture. How probable was it to find those results? And then very quickly here in the end also, just to introduce you to this idea of all the tests that we do, and if you use statistical tests, they do have assumptions, and we certainly have to meet those assumptions. Okay. Sharing my screen. I'm saving all of these, and then we'll send them. We'll send these filled-in exercise, new exercise sets to you as well. Good. Emil, anything from you?
No, nothing. Thank you very much. Guess I'm going to finish a little bit early today. And if there's any last questions to ask, Kanshu isn't here at the moment, so yeah, any last things?
So I see there, as a financial aid officer at COFSIS, go COFSIS, I can already see how much this can help our department. I'm a novice, but I'm impressed. Yes, the data science impresses all of us. It really is it's daunting in the beginning, but I'm so, you know, I'm so thankful to see so many of you here, because I can well imagine what's going to come of all of this, where you're going to take this. This week is just your first tiny little step, but I really look forward. One day when I'm old and gray, perhaps you walk past me and you say, look at this wonderful thing I did, and it started by just being introduced to the topic as you were introduced now. I look forward to that day.
As Kanchu said, people are stressing a little bit about the code for the quiz at the end of the week. Please don't stress about the code. There's not going to be I don't think there is going to be any coding questions.
There's certainly, yeah, there is. Sorry, Emilia, there is going to be, but I mean, none of this is going to be rigorous. There's not some high bar that you have to pass. We all understand the fact that if this is the first week that you're seeing code, that's impossible to do, to write, some long lines of code and try and express yourself properly through the code. That's not humanly possible. And we certainly won't expect that of you. The whole idea is for you to write a few lines of code just to start. It's just like breaking that barrier of starting to write code. And that's all we want to see. And that should be out tomorrow. And it's certainly, as Emil now said, it's certainly not going to be it's not going to be taxing at all. It's just sort of bringing some of the ideas, and it's just also there just to make you think. Just to start thinking about stuff, starting this idea of computational thinking, because data science and computational thinking, the 2-year-old department, for me, it's much more about that idea of computational thinking, how to have these thoughts in your head and just to transform them into a bit of code. Thanks for me.
Then there's a constant ask of these live sessions. When will we put them online and make them available? Will we make them available?
So would that is that referring to videos, the video recording of these Zoom webinars, or the actual code?
Yes, both.
Both. I don't know when Kanchu is recording all of these. So everyone filled up his inbox, and so now you can fill up his inbox more. Ask him when he'll make these available. Look, listen, Kanchu's incredibly leading this school for data science and work. So I'm sure he'll get it out as soon as possible. And then these, I'll speak to him just to see, because I thought about just finishing all of them and then sending them out, but we might as well send them out one by as we finished each day. So I'll speak to Kanchu afterwards, and as we can upload them, we'll let you know where these completed are. But I'm sure Emil is impressed on you all the time. Go Google the answers. All the answers are out there. You'll find them.
And also having this week's exercises somewhere saved on a folder in your desktop is definitely something that I'm going to do, because a lot of the times you can just go and copy paste some of your old code, especially when it comes to making graphs. Those are very taxing to have to remake from scratch every time. And so just to have that code at hand is very, very helpful.
So I like this comment here from Pedri Claessens. Pedri, you say in loads of applications, they just pump out ANOVAs or t-tests. How do you trust the testing of normality if not mentioned? So once you get into this world of data science and you start following people on YouTube, on Twitter, and you watch some YouTube videos, become part of this community, you'll see that this is a very valid question, and it gets asked all the time, and it's getting more robust. We live in this world where we have peer-reviewed journals, so your drafts will be sent to some anonymous peer reviewers. They look at it. Number one is they don't have access to the data. They don't have access to your analysis. They are obviously, I mean, I'm a reviewer for quite a few, and I'm on the board for a couple of journals. I know how this works, and I know how we're trying to change it. And as much as we want the data, and we want to see how the analysis was done. And some journals are becoming like that you have to hand in, otherwise you won't get published. And otherwise, what does peer review mean if someone didn't see how your analysis was done, didn't see the data, couldn't replicate it for themselves? There's this huge big hole in publications and peer review, is this ability to see how things were done. Of course, the saving grace that we do have is that many people are about publishing papers to reproduce previous results, and if previous results are reproducible, it builds that, and that's why we look for review studies these days, amalgamate a lot of tests, a lot of previous publications together, etc. But Pedri, you are, it's a very valid point you're making there. And the world is changing. And I think it's because of the empowerment of everyone having the ability to use a tool like Python or these other languages and being involved in what we would term data science, that everyone's becoming much more aware of this. And I think, you can clearly see that there's from the journals that I'm at least part of, you can see over time how the quality of things are starting to improve. So if you were to look at these metrics, depending on the field, etc., and what goes on, there's certainly more people understanding what is going on and being aware of these things through data science and these tools. Things are certainly improving.
Timothy asks if you can share this website with your friends and family. I think it's public, so I guess you're more than welcome,
Yes.
but just obviously not getting the certificate for the course, which is
Yes.
good for the CV, and then try and sell it to as many people as you can so we can get more people next time.
Yes, so this was a free course, of course, and you'll see that I put out most of the education material that I do is out available free of charge to anyone. And this is on Twitter, you'll see a hashtag OER, Open Educational Resources. So that's also a huge movement throughout the data science community, is to put out these resources for anyone to take advantage of. So most definitely show that to anyone. So Rebecca. Okay, so Rebecca, yes, that's a good question that you asked. There's actually a very nice piece of software called Orange. And if you look through my YouTube channel, just look at the recent uploads. If you go a couple of videos back, I don't have the link right here in front of me. I've put out a couple of videos on Orange. Now, what Orange software does, it actually runs Python behind the scenes. And it's these blocks that you drag onto a blank canvas and you connect the blocks up. And it generates Python code for you instead of you having to write the Python code, although there's blocks that you can drag on that allows you to do the Python code as well. But it actually does, it's pure Python, it's 100% Python, but done very visually. And some people find that a very nice way to start data exploration. And when you watch my videos on Orange, you'll see that even in my research units, where you do use Orange, it's just for that initial data exploration, because it's very quick to do, And immediately you get the summary statistics, you get the visualization and a couple of results, and you start to understand what's going on before you do any kind of deeper work. And that's very much still, it's 100% open source, 100% Python, and basically exactly what we've discussed here, just very visually. So just have a look at one or two of my videos and just search for Python and Orange, and you can install that on your computer. And that's a very nice, a quick way. And what we do also in the research unit, if we have some collaborators, junior collaborators, they know nothing about data science or any kind of analysis, it's also a very nice way to bring people on board, just with very quickly understanding what is going on, is to use that visual version of Python.
So it's a very open-ended question from Hannah, asking how to make a standout solution when it comes to data science. And I think it's very difficult to answer these types of questions, but you have to be very creative when you look at your data. You obviously have to do all of the normal tests like the ones we're doing here today, but if you want to really stand out, try and understand the philosophy behind the data and really try and be creative in your solution, if that makes sense.
Yeah, what you need is, you obviously need a very good supervisor. And the problem that we also deal with, a very big problem in resource constraints environments, is that your supervisors are busy with other things because there's just not many, as many people as you have in big research units, perhaps in Northern Hemisphere neighbors in certain countries, but even they struggle. But here in South Africa specifically, we struggle when it comes to supervisors. Unfortunately, some people are horrible supervisors, and it's just not because they want to be, it's because they're so busy and overtaxed with other things. But what you want to find is a very good supervisor. That makes all the difference.
Yeah, if only we could all have perfect supervisors, but
So Chloe, yes, most definitely. Chloe, maybe you should contact me after the fact, and we can have an offline chat about that. Data science is also, if there's a field that takes up things very slowly, it's the healthcare field. People in healthcare, and I can say that because I am one, are sometimes a bit slow, very particular in the way that they've always done things, and we will not change. And now I'm being facetious, and I'm making fun of myself. Slow to take up new things. So in data science in the healthcare world, some other areas are taking them up much quicker and easier. There's always a bit of a struggle when it comes to new technology, but there's people doing tremendous things. So yeah, I'm again stretching the truth a bit just to make a point. But they're in saying that it is sometimes difficult, but some people are doing incredible things, especially when we talk about machine learning. Certainly my particular field. And so maybe afterwards we can have a chat, Chloe, if you want to reach out to me specifically.
Some of the trending topics for PhD in data science. So it's very difficult. Most of the topics across all of the faculties are using data science. There isn't one specific field that's going to be a bit more trendy than the next. I think at the moment, the kind of AI computer science part is getting quite a lot of attention, because that's pretty much where most of the technology lies. And trying to improve that is obviously going to be very beneficial and create a lot of money. But then actually using data science, find the data that you love, and then apply the science on it. Every single faculty can work with data science, and so there's no specific trendy topics. For example, we've got postdocs next year at the data science schools. It's going to be studying sports data to try and improve. So for example, in the Premier League, they use quite a lot of data science to make sure that all of the players don't play for too long, so they actually can predict when a player is supposed to be taking a break before they get injured. And so we're going to try and have a postdoc that kind of studies that kind of stuff next year. So yeah, just try and find your topic of interest, your love, and then do what you want.
You can
and then
So Emilia, I want to support what you're saying there. You can literally do anything. In my personal work, I'm also doing work on renewable energy. So predicting when the solar panels are going to fail, predicting demand. It's just everywhere. There's just almost no field that is untouched by data science and machine learning.
And furthering that onto the business side, data science is becoming very popular now because it's being used heavily in the business economics and trying to understand transactional data, and the banks are using all of that. That's why everyone's trying to collect all of our data from how we use it on our credit cards or debit cards, and how we spend at Checkers. For example, Checkers is using data science to to know when it's best to put out specials. So all the specials that you see on the side, they use data science to figure out what's the best times to do those specials. And so business is definitely becoming very heavily on the data science side as well. On the point of electrical engineering, so I'm very much part of the machine learning side. So I'm kind of in between electrical engineering and computer science when it comes to my PhD. But it's very beneficial to have an electrical engineering background, because most of the data that is going to be collected, this is maybe outside of businesses and stuff like that, maybe more of collecting data with physical devices. If you're part of the process of designing those devices, then you're part of the data collecting pipeline. And having that knowledge and background is very beneficial, because then you can understand the data obviously a little bit more, because you designed the thing that's collecting the data. So for example, if people are collecting data from whales, they're going to put sensors in the bottom of the ocean. The electrical engineers that are part of that are going to be directly involved in the data science part of the project as well, because they're obviously right there. They know exactly how the sensors work. They know exactly how the data looks, and what they're looking for. but I'm more on the machine learning and the AI side. I'm trying to make neural networks a little bit cheaper and a little bit better, a lot cheaper and a lot better.
I wish you well, Emil, because that's certainly a very important goal that you've set there for your PhD. Hi, Dr. Klopper. I checked you out on LinkedIn. I saw you involved in the medical field. Yes, I am a surgeon. And how did you become data science? I think I can call myself one of those Steve Jobs people who medicine, especially surgery, eat up your whole life. It is a dedication, and all of this developed outside of that. But I think yesterday I mentioned it all came via the mathematics, and the Steve Jobs part. What I mean by that is I just attended the mathematics courses that I felt like. So we're talking about all your different years of calculus, differential equations, linear algebra, abstract algebra, all those fields to study what I wanted because I love mathematics. And it is possible, of course, to do that at a university. And it's through my love of mathematics that I got involved with data science. Would you say data science is similar to actuarial sciences? Well, certainly the life tables, we work on that as well, Cox regression analysis, and those kind of things. Certainly in the actuarial world, machine learning, instead of using those old, more traditional approaches, let me call them that, it's certainly also becoming used quite a bit. I think that's it, Emil. I think we've got to go and have some have a coffee.
Or a beer. We're finally allowed to drink a beer.
Enjoy your beer.
All right. Thank you, everyone. See you guys tomorrow. How do I end the entire meeting? I think Kanchi was always doing that, so I don't know how to do that.
I don't know. I think if everyone just says logs off, I think that'll probably do it. Thank you to everyone for being here. Thanks for all the well wishes.
And yes, happy birthday, Johan. Sorry.
Thank you. Thank you very much.
Enjoy your evening. Cheers.
Cheers. Bye-bye. Bye, everyone.